Alright, so let's talk about the limit definition of the derivative versus just derivative rules, using the limit definition versus rules to differentiate a function. What's easier? Well, obviously the rules are going to be easier, but I want to really illustrate that. So this function that you see down here, f of x equals 5x squared minus 3x plus 7, this is from a video I've done earlier on this playlist, the derivatives or differentiation playlist on my channel, and I use the limit definition of the derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h to arrive at the derivative of this function. Now, the derivative of this function is just 10x minus 3, and if you know derivative rules, if you're even relatively comfortable with rules for taking the derivative, you can look at this function and say, okay, what's 5x squared minus 3x plus 7 prime? Okay, well, that's just 10x minus 3. You can come up with that in nothing flat without having to do any work. So let's go over really quickly what we had to do when we use the limit definition of the derivative. Well, we had to remember the limit definition, which is this giant, ugly formula. All of this right here, and then so we had to start plugging things in, and we need, okay, wherever there is an x, we're going to plug in an x plus h for this first part, and then we're just going to rewrite each part of the function for the f of x portion, and then we're going to let h go to 0, so it's never really 0, but when we get done with the function, when we get done with using the limit definition of the derivative to differentiate this, we're going to sort of treat it like 0, and it will go away. So it's just, there's a lot of work there. So we started plugging everything in. I mean, look, this is just monumental. This is not fun at all. So you can start getting frustrated pretty quickly. Look at the room for error that we have. First, we have to plug everything in to this part, and then we have to make sure that all of this translates nicely down here, that we didn't make any mistakes in copying things, we didn't make any mistakes in factoring things or just multiplying things out, moving terms around. And we have to continue doing that and make sure we pull out h's, and it's ugly. So this is a lot of work. The video where I did this took about 9-ish minutes, I think. So had I just, quietly, without explaining anything, done this, it probably would have taken about 5 minutes of just algebraic math, and that's a pain, so why should we do that? Well, look at our initial function. F of x equals 5x squared minus 3x plus 7. So let's get a new page here and write this. F of x equals 5x squared minus 3x plus 7. So this is our function. Now, what are some derivative rules that we can apply here? Well, we can apply the constant rule that says c prime is always 0. Well, what does that allow us to do? What constants do we have here? Well, 7 sure looks like a constant. I'm sorry, let me rewrite this. Looks like garbage. C prime is always equal to 0. So what constants we have here? Well, 7 looks like a constant. So since it's 0, we know that this function, we don't need to worry about it. 7, we can just delete it. So now all we have to even worry about is just 5x squared minus 3x. That's all we even have to concern ourselves with, because the 7 is gone. So what can we do? Well, we can remember this, the two rules here. We know that a constant times a function prime is just the constant times the function prime. Well, what does that allow us to do? Well, that lets us say we've got a constant times a function right here in the negative 3x. This is a constant times a function. So we can, let me erase here. Well, what we can do with this is we can say, well, we know that it's just going to be, for our final derivative, we have this here, we know that f prime of x is going to be something. We know that 7 doesn't matter, so we can say it's going to be something minus something plus 0, right? Well, this something right here, we know it's going to be 3 times something, right? So constant times the function. Well, since our function here is just x, we can remember that x prime is always just equal to 1. And so this is 3 times 1 plus 0. And then we have 5x squared. We can remember the power rule. Let me rewrite this. 5x squared. We can remember the power rule. And the power rule says that x to the n prime, I can't write, which is, if you've watched any of my other videos, that's probably pretty obvious to you by now. X to the h, x to the n, that's an n, we'll just pretend. X to the n prime equals n times x to the n minus 1. So we can just bring this 2 down here and multiply it times 5, so that's going to give us 10, right? And then we have to the n minus 1, so we're going to be subtracting 1 from this power, so it's 2 minus 1, so it's 10 to the first. So our derivative is 10 to the first minus 3 times 1 plus 0, so our derivative is just 10, I'm sorry, not 10 to the first, 10x to the first. Careless errors there. So our derivative is just 10x minus 3. Now wait, look at that. How much work did that take? 10x minus 3 is our derivative. And that took about, I don't know, of actual work, maybe 2 minutes. But if you know these rules in your head and you can just start seeing things, then it takes you maybe 3 or 4 seconds to do that derivative. So look at all this. 10 minutes of painstaking, algebraic, miserable work. Or we can come up with the exact same answer and not even have to rely on the limit at all. Not even have to worry about that and say, okay, here's how I would look at this function. If I understood my rules and didn't have to write them down, if I understood them relatively well, I would look at my function. I would say I've got 5x squared minus 3x plus 7. I would say, okay, 7's a constant prime, that's 0, minus 3x, well, that's just, x just goes away because it's 3 times, it's a constant times a function, x is always 1. This 2 is going to come down here and be multiplied by 5, so I'm just going to get 10x minus 3. That's how long it takes. Even less than that. So that's the beauty of being able to use derivative rules as opposed to the limit definition of the derivative, because there's just too much work involved in the limit definition. It's good to understand the limit definition because it makes a lot of sense. If I just say, oh, well, a constant prime is always 0, yeah, that graphically, and pardon my aside here, that does make sense because, okay, like here's f of x equals 3, right there. Well, what's the slope of this line? Well, it's just 0, so f prime is 0, and that makes sense why that's the case. But some of these rules, okay, like the x to the n prime is n times x to the n minus 1. I can tell you that, and you can take me on faith, or you can try to prove it using the limit definition, but it's not intuitively true. It doesn't just make sense immediately, even though it is true. So the limit definition is a good thing to know because it explains and proves why things are true. It makes sense on the graph why they're true that way. When you rely on the limit for the limit definition for your derivatives, but once you understand that, there's really no need to use it at all. So this using rules is going to be what, if you continue watching this series of videos, what we're going to use for everything. Limit definition won't resurface again at all, except maybe only in a minor aside. So using these rules is a much easier way to get to things. And look at that, 10x minus 3 is our derivative. We're good to go. That's all there is to it.